Good morning. My name's Martin Robinson. I'm the CEO of Iris, and I'd like to welcome you to the second webinar in our Bridging the Gap series. The first one we covered the skills gap that we're currently experiencing. This one we're going to go over what we class as the maintenance gap and where we look at moving from a time-based or calendar-based maintenance platform to a condition-based or reliability engineering-based maintenance platform. Now, when we look at electrical systems, obviously they're very critical to every part of industry. As I've gone on before in some of the webinars, I've discussed that our mechanical systems are and maintenance practices are far more mature than our electrical systems. But in the last sort of 4 or 5 years, these electrical maintenance platforms have really been given a lot more precedence, and now we're starting to see some real moves from traditional calendar-based maintenance on electrical systems to a condition-based maintenance platform. So I'm going to sort of discuss some of the points that you really need to review as you take this journey. Now, like with most things, it's always safety first. And electrical systems are very dangerous. Now, if you look at this triangle here, this is a standard health and safety triangle for a traditional maintenance platform, non-electrical, where when we look at this, you're saying for 300,000 at-risk behaviors, you'll see 30,000 near misses, 300 recordable injuries, 30 lost time injuries, and that would lead to 1 fatality. Now, when you compare this to the electrical safety pyramid, you can see that for every 10 recordable injuries, that can lead to 1 fatality. So that's a 301 in a normal workplace versus 10 to 1 in an electrical workplace. So what that basically means that it could just for every 10,000 electrical at-risk behaviors, you can expect 1 fatality. And electricians do things every day that are super dangerous. I mean, opening panels, racking in that brake. There's lots of things that we do that are out of the norm that we could class as an at-risk behavior. So when we're looking from a health and safety standpoint, what we're going to try and do is reduce the amount of at-risk behaviors, which in turn will reduce the amount of fatalities that we should see. And again, these are very high numbers. I mean, if you look into the electrical safety fields, I mean, you hear things like 5 to 10 arc flashes a day, 250 to 300 fatalities a year in the United States alone. We're grateful that these numbers are on the decline, but they're still far too high. Now, there's a whole bunch of regulations and standards that are available to you when you're looking at electrical safety. OSHA, NFPA, National Electric Code, etc. There's a whole bunch of support standards from places like IEEE, NFPA, IEC, ANSI, NETA. All of these organizations have a bunch of support standards that supply the regulations. So there's a lot of information out there that can really help you out. And again, one of the, I suppose, the most prevalent ones, especially here in the United States, not so much if you work outside the United States, but I do see it being used as a seed document in many international standards, is the National Fire Prevention Association 70E, which is basically the standard for electrical safety in the workplace. And what that strategy is all about is creating an electrical safe work condition. In the current one, they discuss training, planning, hazard assessment, engineering, PPE, and tools. So it's a great document to actually use for reference, and in 2018 it actually went very heavy on risk, and we discussed this in our previous webinar. So what are electrical hazards? What do we face when we do this? Well, basically we're looking at electric shock, fire ignition, arc flash, and arc blast. So these are the electrical hazards that an electrician could be placed at when working on energized equipment. Now, common conditions that may increase the hazard is elevated location, obviously working on a ladder, or working in a confined space, which are both areas where electricians find themselves routinely. So not only are you faced with the hazards, but then by looking at these, we're going to elevate that risk level. And then the possible results, obviously, from direct contact is electrocution, internal, external burns, or indirect like falls, smoke inhalation. So again, as I stated earlier, the electrical engineer, the electrician, works in a very, very dangerous locations. One thing you've got to remember is there's a lot of other hazards that you're going to find on the job. Things with chemicals and lighting and pollution, etc., etc. So, although we tend to concentrate on the primary things that an electrician might face, there's all of the other things that are more occupational health and safety based that you must be aware of. So, safety never ends. Remember that if you are at all unsure, look it up. Most of these regulations are available to you as reference documents online, but they are inexpensive. At nfpa.org, you can buy all of these documents in the PDF version as well as hardback, but they are there for you to use and they are there to ensure that you work safe. Now, once we've made up our mind, or we're looking at trying to move from a calendar-based maintenance system or time-based maintenance system to more of a reliability or condition-based system, we start to look at things like these cycle curves or life cycle curves or innovation curves. They're called lots of different things. But there was a guy called Jeffrey Moore. I read a book of his called Crossing the Chasm, where he took a really unique look at how do we start to make these changes and the steps that we go through. Now, looking at a management life cycle, you go through several stages of adoption. First and foremost, they're the innovators. These are the people that are going to start to look at. They're the techno buffs. They really want to look at things. They're innovators, as it states in there. They're looking for systems or solutions to their everyday problems. So these are the first guys that will take hold of any management system that you might put in place, look at it and help you. These are real guys that are going to push you along. Now, the next guys that would come in there is what we class as our early adopters. Now, they'll help you really start to push your management system towards the brunt of the population of your group. They all see the potential in systems. They're always willing to help you debug and tweak and make subtle changes so the system starts to work for the work solutions that you're looking for. The next guys we start to look at is what we call the early majority. Now, this group are far more pragmatic, and they're looking for solutions to their everyday problems. But they'll only buy a finished product. Unlike the early adopters and innovators who are part of helping you to develop your system, when we start to get into the early majorities, they're looking for finished product lines, no beta versions of anything. The late majority, they're basically what we call the primary objective really is the avoidance of risk. They're jumping on the bandwagon, some might say, of the work that's been done through innovation into the early majority. But again, this is they're more conservative, should we say, than those in the early majority group. And then finally, there's what we call the laggards, and these are the skeptics. They're only interested in the system after everybody's done it, after it's been tweaked, probably its fourth version down the line. And again, these are like the last ones to really adopt anything you might be coming up with. So when we look at the management life cycles, the life cycle really is nothing new. We've seen these sort of things for years, and these can be a product, as I say, or a system or whatever. But these adoption life cycles are pretty similar. But where Moore made the difference, he started to look at things, and what he sort of discovered was there was an existence of a gap between early adopters and early majority, and what he calls the chasm, a very deep chasm. And basically, his book was, bridging the chasm. How do we cross this chasm to go from early adoption into early majority? And he came up with a number of solutions or scenarios for us to consider. Now, as we sort of think, the chasm really starts to exist after a certain point. Once you've really come through the early adopters, you tend to what we class as plateau, and this is where a lot of systems struggle. This is where the implementation fails, where we don't take into account that we have to bridge this chasm before we get the system into the masses, if you like. It takes the adoption up. So early majority is pragmatic, as we said, and will only accept the system if it solves a current problem they face. So again, they're possibly not worried about return on safety, return on investment. They're looking at solving a problem. They're in electrical systems. They might have had an accident. Someone might have been hurt or injured, or a system might have shut down. So they're looking at changing the way they're doing their electrical maintenance from the calendar-based to condition-based. and they're looking at the practicalities of that system, and how does it meet their requirements. There's a whole bunch of things you have to consider before you really start to push across from the early adopters into the early majority. Now, more come up with a number of points. There's a number of things that you really need to do or consider before, to successfully cross the chasm. Number one was you must create a whole system, a whole management system. Trying to cross the chasm without a complete feature set and all the major bugs eliminated is going to be a problem. They don't want beta versions. They want a finished system, okay, tried and tested. You need to position the management system appropriately for the skeptical pragmatists that make up the early majority. And that's, when we're talking about if you have a system that is meeting a practical requirement, then that is a big thing that's going to really help you get in front of this early majority. Cost justification of the new system relative to the current system being employed. Now, I know in the last slide, ROI and ROS are not the most important things, but once you've showed the practicalities of what you're going to be doing, then you will not need to start to discuss, the actual cost justifications of the new system. If there's a capital expenditure required, then you need to make sure that that's cost justified and the ROI for that cost justification is laid out. And then finally, it says, you must introduce the management system through the right channels. There's no point in me introducing, a calendar-based maintenance system across to a condition-based maintenance system to the management chain without the backup of the early adopters in that, who would probably be the maintenance department that we've been working with to produce these systems. So make sure that when you present it, you present it in a way that it physically makes sense to the people that are looking at it. So when we look at traditional electrical maintenance practices, the traditional way of testing things, we do more hands-on. So it's calendar-based, tightness and torque testing, mega testing, stress testing, circuit testing, load bank testing, breaker and isolator testing, etc. So this is sort of done thing, but again, these maintenance tasks are designed for one outcome in mind. What you're thinking about is we need to confirm whether or not the circuits or connections are good. So in maintenance, what we're trying to look at is we're looking at the system, and if we can confirm that the system is meeting the operation requirements and is safe, then really that's all we need to do. So there has to be a better way, and there is a better way of doing this. So in our last presentation, we looked at the electrical failure modes, where we looked at a good electrical circuit versus a high resistance or loose connection, loose lugs, overloads, partial discharge. We looked at all of these failure modes and the condition-based equipment that can identify these failure modes while they're online, fully energized. So the thing then we looked at is what we class as return on safety. Yeah. So when we look at return on safety, what I'm trying to show is if I'm going to implement a safe practice and safe work and it's going to cost X, what is the return on that? Well, what we broke down into is we looked at on the OSHA website the average cost of an electrical injury. And what OSHA states is basically with the direct and indirect costs, the total average cost of an electrical injury is $181,708. That's the total average cost of an electrical injury. Now, if we look at the average US company profit margin, again, it's approximately 6%. That basically means that the earnings to cover the direct cost of the injury is $1.4 million. Yeah? The earnings to cover the total cost of injury with a 6% profit margin was over $3 million. So the average electrical injury is $181,708. The average earnings profit margin is 6%, so that means I'm going to have to find $3 million of income to cover that accident. Now that's a big number. So when you look at your ROS calculations, let's say we look at an electrical maintenance safety device program cost where we're going to put in maybe some inspection ports, some monitoring systems, some sensors, some equipment, some training. Let's say we put $50,000 into our safety platform. That will give me a percentage risk reduction of 75%. So I'm not going to say I'm going to remove 100% of all the risk, but by implementing that $50,000 EMSD, electrical maintenance safety device program, at 75% reduction, that's going to give me a cost avoidance benefit of $136,281. So I'm saying I'm going to reduce the likelihood of that accident by 75%. So with that cost avoidance benefit and what the actual cost of the program is, I'm seeing a savings ratio for each dollar spent of 2.73. So all of these numbers are available. I mean, this isn't just Martin Robinson sitting down and pulling numbers out of his hat. If you go on Google or any of the search engines, you can search these parameters and use them yourself. But people are really starting to recognize that by implementing a safer platform, we're saving a lot of money. We're saving a lot of money. Another area where we covered in our last webinar, but I want to go over again because it's very important, is risk. Risk is a huge driver of where and when we spend our money. So once we've calculated our risk numbers, and we know what the risk to the business is, the criticality, etc., then I can use that risk and criticality assessment to dictate how often I do my maintenance. Therefore, something that's not critical may only have an annual inspection, where something that's so critical, we might want to put online monitoring systems in there. We might want to be doing monthly inspections. There's all sorts of things we're going to do when we start strategizing to come away from that calendar based to a condition based. How often are we going to do it? How are we going to do it? What are we going to do? So again, criticality and risk are massive drivers to determine the level of expense on the different types of strategies that we can implement for our maintenance platform. So what do maintenance management systems require? Well, I look at documents from all over the world, the United States, Europe, Canada, Latin America, etc., and they all tend to have the minimum requirements for a successful and safe management system. First of all, they look at compliance. So you must be in full compliance with any local existing statutory requirements and local regulations maybe that are driven by your company. Secondly, the maintainability. Systems must always be safe so that no system or part of it may give rise to danger during either normal operation or under fault conditions. Another area we look at is responsibility. There must be accountability for designing and implementing adequate maintenance management programs. Regular assessments, the needs and the frequency requirement of the testing, maintaining and monitoring of the systems and equipment. Again, documentation is key. And most standards, I think virtually every standard I've ever seen, huge on documentation and keeping very detailed documentation. Now, the management system must ensure that adequate records are kept of all maintenance activities and the results of all testing and their data collection programs. So these are sort of the core concepts of most management systems. A term you're going to hear a lot is reasonably practicable. And where they say that risk should be set against the effort required to remove it. So it is not reasonably practicable for the cost of removal of risk is disproportionately high. So again, if it's reasonably practicable, if risk can be removed at minimum cost and effort, then you tend to get the buy-in to a system, okay? But then if it's not reasonably practicable for us to do something, then we have to look at other ways of removing risk. But again, this is a term that you hear many times in many standards, reasonably practicable. Now in IRIS, we have a term we call critical asset surveillance technologies, or CAST. And CAST is our way of adopting not just maintenance practices, but also giving you these safe systems of work that enable you to get the data, etc., that you need. Okay, now there is a standard under SAE, which is Society of Automotive Engineers, JA 1012-201108, is a criteria for the technical feasibility of an inspection technique. Now, what this standard states is, can a potential failure condition be identified? Can the degradation interval be defined? And again, in electrical systems, they tend to have a steady rate of decay on most systems. That's why it's nice to have routine condition monitoring of these systems. Can the degradation intervals is relatively stable? Yes, it is. I just said. A task can be performed at intervals less than the degradation interval. Yes, they can. The reaction interval is long enough for a predetermined action. So, for instance, if I find a problem and I know the state of that problem, can I fix it quick enough before it fails catastrophically? And again, yes, you can. So, and can the safety, environmental, and economic, remember that reasonably practicable, the economic criteria are met. So, CAST inspection models meet the requirements of this JA1012. And again, so therefore, when you're looking at building your own systems, you can utilize the requirements of SAE, which is what reliability center maintenance does on the JA1012, to meet the requirements. And so then you have a feasible inspection technique. You cannot solve a problem with the same level of thinking that created them. So we say the same old thinking will get you the same old results. Now, I was in the military for a long time, and as military engineers, we were trained on the KISS principle, the keep it simple, stupid. Now, this doesn't imply that you're stupid. What it basically means is that we're going to take a complex system and simplify the actions of that system. So again, as Einstein said, that everything should be made as simple as possible, but not simpler, which means that you should simplify a design of a product, and success is achieved when the design is at its maximum simplicity. So we use CAST and EMSD technologies to take these complex requirements of an electrical or mechanical system and put in the inspection techniques and data collection methods so we can maintain the equipment and manage the risk of that equipment failing. So the CAST program is built into 4 levels, which we're now going to go through in greater detail. So when you look at a CAST program, basically we look at data collection. Now, data collection is the routine data collection from equipment using condition-based monitoring devices such as infrared cameras, ultrasound devices, partial discharge devices, maybe vibration analysis, oil analysis. This is all about data collection. Now, what we're trying to do now is break down the required skill levels, so that, again, we went through in our first webinar about the skill shortages and how we can break this down. So the first level in the CAST program is the CAST technician. This is a guy, probably entry-level guy, minimum skilled electrical engineer, etc., who's really going to be responsible for most of the routine data collection. This technician basically attends a 3-day course where we go through environmental health and safety, introduction to reliability maintenance. We discuss failure patterns, failure modes, PF curves, etc. We go through an introduction to CAST technology. So we give them a broad brush understanding of most of the condition-based monitoring technologies with very heavily reference on the infrared and acoustics. Now, we do some mechanical systems like this, and we might go very heavy on the alignment and vibration and ultrasound. But we go over enough so the technician is confident using the equipment. We then look at implementing a CAST maintenance program, the route selection and data management, the electrical maintenance safety devices, inspection systems, IoT solutions. And the student will have to complete, pass a written exam, pass a proficiency test, and pass practical tests. Now, this is what we do for a CAST technician. But these can be internal programs. Just put your structure together, put what you want them to do. You can get internal or external resources and build these programs yourself. This is just a suggested platform. So the data collection piece, as we said, is done by minimum skilled labour. So typically maybe entry-level electricians, or you might have apprentices that do this type of work. Again, routine, but must be done. Okay, now the next part really of the EMSD program cycle is diagnosis and repair. Now this is where this is your traditional level 1 infrared thermographer, ultrasound guy with a bit of experience in the tools, etc. This is where they get involved. So we bring them in at this point. So we split the technician requirements to infrared or ultrasound, one or the other, again, and they do a traditional level 1. You'd bring the guy a 4-day training course, technology overview, whichever discipline they're utilizing, basic electrical magnet safety device installation training, so how to install and use EMSDs. So the course, this is designed, for hands-on experience, so they can basically confidently install and use EMSD type products, get them used to the IoT sensors, solution based, that type of thing. Again, the student has to complete a minimum of 200 hours. So when you're putting your program together, make sure you look at make sure they spend some time on the tools and they don't just do a level 1, level 2, level 3, I know it all. A big part of learning this job is the time you spend doing the job. So you need to have a minimum amount of hours. We recommend a minimum of 210 hours between doing a cast technician and a level 1 cast training. Okay, you have to pass an exam, etc. So this is basically your traditional level 1 ASNT or ISO based training course. So from diagnosis and repair, the next thing we're looking at is what we call duty cycle commissioning. So once this is all the work's been done, what we tend to try and do, if possible, depending on the size of your organization, is have another guy who's responsible for coming and testing and putting the thing back on cycle. Okay, this is your traditional level 2 technician. And basically, a level 2 cast technician must have level 2 overview on the technologies, advanced EMSD training. You're looking at, again, at least another 420 hours on the tools, must have done the level 1, must pass the proficiency test in the chosen technologies. And again, this is the guy that then is responsible for checking that the maintenance has been done correctly and put it on there. Depending on the size of your organization, one guy might do both. It just depends on how you want to put your management system together. The next final part, if you like, is what we call program management. So who's responsible for managing all of this data, making sure the work's done, making sure that the data that's collected routinely is processed correctly so we can find issues and schedule the diagnosis, repairs, and back on cycle, etc. So this is typically what we call a master technician. So this is a guy that really would probably be, what we used to say as a level 3 infrared, etc. Our system is a 5-day training course, advanced cast program management, advanced infrared training, advanced ultrasound training, advanced cast inspection technologies. Must have had a minimum of 630 hours as a hands-on level 2 or level 2 technician, and have attended must have had have a CRL or CMRP. So a reliability program training course is a big proponent of this. So again, this is just a structure that we've put together, but I think you can see that it's reasonable for you to look at your own requirements and build your own management system that meets your operational requirements, and then you can go back on some of the technologies, and you can build into traditional level 1 and level 2 into your training platform. You might not want to expand out into these other technologies, but this is, as I say, just a framework for guidance more than anything. And again, once you've done it, back in cycle, and here we are, the data collection routes again. So that's what we call a cast EMSD program cycle. Now, the EMSDs are making sure that this is done routinely. Nobody is opening panels. Nobody's trying to put their head in things they shouldn't do. It's what we call mistake proofing. We're trying to make sure that nobody can hurt themselves, but we need the data to make sure that everything's running as it should be. So the cast training summary, basically, we're looking at taking entry-level personnel, taking them through the concepts of asset reliability management, data collection techniques, etc. It's basically, I suppose, the journey. I'm very big on making sure that we train the guys, that they understand the program, understand the journey, what the management output is, what we're looking for, what's the vision on this platform, what we're trying to achieve. If everybody is aligned to that from day one, then implementation is easier, acceptance is better, and then the programs tend to fail less. But again, most of these programs fail on the early days of implementation and nobody being told exactly what we're trying to achieve. So common ways in which we interact with equipment, so an electrical hazard is a state that occurs when exposed parts are present, or when you're interacting with a piece of equipment in such a way that you could be electrocuted or cause an arc flash. And so this is things like opening doors, removing and replacing covers, reaching in and out of equipment, removing and replacing internal barriers, operating switches, racking breakers in and out, using tools or test equipment. These are all conditions that can cause a hazard. So we're trying to look at ways of taking those out, but still getting that data. So the maintenance inspection systems, or I suppose people used to call them infrared windows or things, but they've expanded so much past that now. We're looking with the onset of IoT-based solutions, embedded sensors in these maintenance inspection points. These have really grown to such an extent that that you basically just got one point of inspection on a piece of equipment where you can take all of your data. So for me, the big thing is, again, harping on about something we went on in webinar 1, but it's really important: the reducing of maintenance-induced failures. Okay, calendar-based maintenance means that we shut things down, we go in there, we tighten things up. A nut and a bolt and a screw and everything can only be tightened so much before they break. They're a mechanical device. So we're saying, using condition monitoring, using the monitoring techniques that we're trying to implement, I will only repair things as and when they need repairing, and I can identify that repair because I know the fault condition, and I know the equipment that I'm using can identify all of the fault conditions that I will see in that equipment. And that comes from our criticality and risk analysis of the equipment, when we look at all of the fault modes, etc., etc. So when we look at types of electrical maintenance safety devices, you've got infrared windows or inspection windows. They can be round or rectangular, they can be visual or infrared or ultraviolet or all of the above, custom designed. There's a vast array of inspection windows that are available. Most people are now realizing that they're not just round and they're not just crystal. There's so many more variations available to you. We're looking at ports, ultrasound ports. In electrical systems, the ultrasound is now being far more widely used, thank God, because it's an excellent piece of equipment. We can find arcing, tracking, and corona using that equipment. There are also things like external voltage indicators, motor current analysis tap-off points, power quality tap-off points. There are standards now that are looking at safety through design, where when we design the equipment, we take every piece of data that we need from that equipment. We should be able to get safely when the equipment in a fully enclosed and guarded condition, routinely under full load conditions. So that's what we're trying to achieve. So ports and windows, etc., are a big part of that. And then finally, we're looking at the industrial Internet of Things solutions, so temperature monitoring, asset tags monitoring, data monitoring, vibration analysis, partial discharge, power quality analysis. All of these things now are coming more and more widely available to the client. So you're utilizing, remember when we do that criticality assessment, we look at risk, high risk, we really don't need it to fail. We're looking at IoT-based solutions that work as part of that. So, in Iris, we've got a whole bunch of windows, but you can customize your inspection system. So you can take a standard window like this, you can build in an ultrasound port, you can build in a data management system, you can build in IoT-based sensors for temperature, humidity, ultrasound, partial discharge. All of these sensors are available to you. You can look at different ways of powering and getting the data back from wirelessly, wired, GSM, local area networks. There's a huge array available to you, and again, it's all based on you, what you require. Okay, you tell the systems providers what your business needs are, and let them provide you with a solution. Okay, and then you're looking at handheld stuff like ultrasound, built-in ultrasound sensors is a new thing that we've seen quite a lot being taken up, built-in partial discharge sensors. So when you're looking at your maintenance inspection system, think of not just what you're doing today, but what you might be doing in 10 years' time, and have a system that is customizable, that will grow and with your business requirements, because what you want today might not be what you want in 5 years' time. The term you hear a lot when we look at electrical safety is the hierarchy of controls. The hierarchy of controls is basically how we categorize risk if you like, within any health and safety situation, not just electrical. So first thing we try and do is we try and eliminate the hazard. Obviously, that's always going to be the most effective way of removing a hazard, is to eliminate it. But what you mustn't do is eliminate one hazard and cause another. That's something you have to be very careful of. Then we look at substitution to replace the hazard with another way of working. We need engineering controls where we can isolate people from the hazard. Administrative controls, we can write work orders that change the way people work. And finally, we look at PPE. Now, PPE is obviously, from a risk management standpoint, the least effective, where the most effective is elimination. So we look at things within this, what we class as hierarchy of controls. Now, when we look at EMSD technologies and the cast inspection models, we work within the elimination and substitution space. The electrical maintenance safety devices are designed to take out the ability of an engineer or a technician to touch or open a panel. They don't have to do that. All the data that they need is easily gathered through an enclosed and guarded solution. And that's what the EMSDs are, and the CAST models are basically the way that we went through earlier of the different levels, the skilled levels to required for data collection all the way through to program management, etc. So when you're working within the EMSD and CAST technology models, we're working in this elimination and substitution space, which is the safest place to work. In the following slides, we're going to look at a benefit analysis of an EMSD program that was installed in a paper mill. This is, we utilize an infrared inspection windows with ultrasound stroke partial discharge inspection ports as well. We looked at the actual program. It was 150 pieces of primary switchgear that were on an annual inspection program. The infrared and ultrasound inspections were completed, fully energized, and in full compliance with NFPA 70E and 70B. The inspection was completed by 2 plant electricians who were required to remove and replace panels, and the contract RCM engineer who was supplied by the insurance company. And the inspections took approximately 150 man hours. Now, what we did, we analysed the energy, the survey that was required with removing panels. Obviously, PPE suit up time, we were looking at approximately 21 days, 2 suit ups per day, 3 guys suiting up, 21 hours of PPE suit up time for the RCM engineer, and 42 hours of suit up for the 2 electricians, which is 63 hours. Now, this was 2 suit ups, but in fact, there was a lot more than 2 suit ups because it was August in a paper mill in South Carolina, which is extraordinarily hot. And we were looking at probably 4 to 6 suit ups a day. You just can't sit in PPE, it's far too warm. The final thing we looked at then is cover removal. So 30 minutes to remove a cover for 2 men, so 150 covers, that's 150 man hours. RCM inspection, that's the engineer going in with the infrared and ultrasound, that was 0.1 of an hour, 15 hours. Cover replacement, another 150 hours. The RCM engineer waiting time, 150 hours. This is the guy sitting there watching electricians put on and put off panels. And then the electrician's waiting time watching the guy do his survey was 30 hours. So the manpower for the inspection was 495 hours. Add to that the PPE suit up time, we had an estimated 558 man hours to do this task. So then we looked at basically, the primary areas of what we were trying to achieve. Now, don't forget, all we're trying to do here now is do an infrared and ultrasound scan, or the RCM inspection, which is 15 hours. Okay, so that's 15 hours. 3% of things what we call productive labor. 97% is dangerous, high risk, unproductive labor. Okay, so that's really, and again, this is not me pointing fingers, this is a process issue, not a person issue. Okay, now with the infrared windows installed, basically no PPE suit up times because the panel is in an enclosed and guarded condition, so we can get all of our data from the panel in a closed and guarded condition. So there's no cover removal. The RCM inspection we gave 30 hours to complete. Cover replacement 0000. So we're looking at the complete inspection, and this was including report generation, is 30 hours. Okay, and that's 30 hours of safe, productive labour. So let's say the man-hour savings went, taking 558 man-hours using a 3-man inspection team to 13 man-hours using 1 inspector. Yeah, real-world savings of 97% on the man-hours to complete this task. So there's a real solid ROI basis on these type of inspections. Obviously, there is a capital expenditure, but the ROI really brings it back very quickly. So in summary, when choosing a condition-based maintenance platform, try and consider the following. Conduct a full criticality assessment of the facility. This will dictate where most of the effort should be directed. RCM, Reliability Center Maintenance, is a really good place to start this journey, because that's really going to help you understand the criticality assessments of your plant and equipment and where you need to spend most of your time. The management system should meet the risk requirements of the operation. Yeah, again, risk and criticality for me when I'm looking at these types of programs are the big drivers for me. That's where I know where I've got to spend most of my time. What's really going to cause me the biggest headache, biggest heartache. Yeah, ensure that your management system meets the legislative and local safety mandates. Again, super important. In the United States, we have things like NFPA 70E, 70B. In Canada, we have CSA Z462 and 463. In Europe, like UK, for instance, we have what is now the 18th edition. All of these things are there to help us out. And finally, train and equip your staff to facilitate the management system. Yeah, most startups fail on implementation. So if you know how you want to do this, you know what data collection points you want, you know how you want them trained and what equipment you want them to use, please facilitate that, because if you don't, then you will fail. Yeah, and as I say, most startups fail on implementation. So again, one of my favorite slides, and I always use it. And again, so without data, you're just another person with an opinion. Data, data, data. That's the big thing. As we pointed out in the CAST model, the data collection piece of this is super important. Okay, very easily managed utilizing EMSDs. I can get guys in there just bringing the data to me on temperature, humidity, partial discharge, vibration analysis. All of this data can come back to me. And then I can start to allocate what resources I do have to repair what needs repairing. So that's the end of the webinar. Thank you very much for your time. I'm now going to take a bunch of questions that I see that are there waiting for me. So thank you again, and let's go to the first question. We're going to go over the question and answer session now that we have a whole bunch of questions here. One of the questions we've got is, or a number of you have asked if this presentation is available. Yes, it is. You can get that online, and we can send you a link to that. So, but the IEEE guys will take care of that for you. Next question I have here is, what is the best way to calculate the risk priority number? Well, the risk priority number, as I laid it there, you can actually look at that for many areas, but we look at it as calculating it from the likelihood of failure, the impact of that failure, and how easy is it to find that failure. So again, we've done a whole bunch of stuff on that. The first webinar went into that in a lot more detail that we did. But by looking at those 3 areas, we find that it's a much better way of coming up with a more realistic risk priority number. One of the things, though, you have to understand is the criticality of that to your system. I see all the time where people put everything at a 10 because everything is super important. So I see a lot of that in the data center world, for instance. And as we say is, be very careful there, because if everything is important, nothing's important. So understand the criticality of that item to your everyday operation and score those accordingly. But by utilizing EMSDs, you're going to, the likelihood of finding the problems, we make it much easier. You haven't got to open panels. And we do a lot more inspections than just once a year or once every 5 years. So we have a significant impact on there by doing routine inspections through EMSDs. We have very low risk priority, or very low risk. So another one I have here is, what's the best way to decide on the maintenance strategy to use? Well, again, it all
revolves around criticality and risk. It depends on how important an item is to your organization. Yeah, if it's important enough that you want to look at it every day, then you will do it every day. If it's something like a pump or a motor set that you have redundancy on, you might have a run to failure option, where you're not even really going to do a lot of maintenance on it, and if it fails, you have so much redundancy in that system and spares to go on it on the shelf that your whatever mechanism you're going to put in place will be decided by the impact to the business. Yeah, so again, for me, the best way to decide on the maintenance strategy is to do a thorough criticality and risk assessment to the operation, and then score everything accordingly, give it the risk RPN number, and then look at your budgets and allocate them accordingly. Another thing, what are the cost savings associated with moving from a calendar-based to a condition-based maintenance model? Well, calendar-based maintenance is cumbersome. I mean, if I look at electrical systems, we've been doing it a long time. Probably, 60, 70, 80 years, people have been utilizing the same calendar-based or time-based maintenance schedule. One of the things I go back to is something like, if you look at your car, if you're as old as I am when you started driving, your vehicles were maintained on a calendar-based schedule. So they would bring them in, and you would basically every 6 months or 6,000 miles, it would drain all the oils, change the filters, change the brakes, etc., etc. It was very costly, and very cumbersome. And if you didn't use your car a lot, you were paying a fortune. And if you use your car, excessively, then again that wasn't enough maintenance. So it didn't work. So what the automotive companies did way back when is they actually looked at condition-based maintenance, and they built into your car now a condition system that monitors itself, and it will come back to you and say, oh, your car needs to be brought in for a service now. So your car may be serviced every 10 to 14 months, depending on its use. So that had significant cost savings to the customer, because they didn't have to change that oil. They didn't have to change the filters. And because it was monitoring its own fault conditions, if a fault did occur, it would let you know. So when you look at the cost savings associated with going to a condition-based model, think of the vehicle you drive today. Yeah, and by monitoring that, there are significant benefits, both financially and operationally, to going to a condition-based maintenance model. Another question we have here is, again, what would you say are the main causes of maintenance-induced failure? I would say over-maintaining. Obviously, you can only, as I said in the webinar, you can only tighten a bolt so many times. You can only tighten a screw so many times. You can only pull on a cable or a connection so many times before you induce fatigue into that unit and it breaks. So by, for using, like, for instance, infrared and ultrasound, etc., looking at electrical connections, if I don't see that there's a hot spot, or I can't hear arcing, tracking, and corona, I see no evidence of PD from a PD scan, physically there's nothing I can do from a maintenance standpoint to make that connection or circuit any better. So where we're coming from is by utilizing condition-based maintenance, I'm not touching the system, I'm just checking it. Yeah, and I'm only going to fix what needs fixing. So what we look at with this system is we go to more of a 100% surveillance repair model, where we're only fixing what needs fixing. Yeah, we're not going in and pulling something apart because a time-based schedule tells us to do that. So maintenance-induced failure is a huge thing. In fact, in 70E, they looked at maintenance-induced failure as a significant issue that we have in the field today. Okay, so we're looking at it. So for me, the main cause of maintenance-induced failure is over-maintenance of our equipment. Another question I've got here is, how do you determine the level required for condition-based maintenance engineers? Well, this is very contentious, and I've had many heated discussions with maintenance guys about skills levels. And I broke it down as, I look at, if I'm looking at a a data collection point, for instance, where I'm going to go and say, okay, if I just need to take the data and I've already predetermined the alarm limits for temperature and decibel levels and PD levels, etc., and I can plug in and write down a number, and I've been shown how to use the test equipment, and all my only job at this level of data collection is to report on my findings, and especially report immediately if they're outside of predetermined alarm levels, then that is the skill level required to do that. Now, for the level 1 and level 2, the traditional level 1 and level 2 guys, that's when we start to look at the background of the guy, the engineer that's doing that. We utilize that background and we teach them up to a level 1 in the infrared and ultrasound and PD and thing. We utilize, say, their background, and then we teach them how to use the equipment. And they take to it like a duck to water, as I say, because they physically understand what they're looking at or listening to because of their background experience. So we have a huge amount of success in getting these more experienced engineers up to scratch as condition-based engineers, because really all they're doing is utilizing equipment to enhance their senses of through sound and vision, through acoustics and infrared, to show them what the faults are. So what we would say is the base level guys, we get to do data collection, which is fairly mundane and can be extraordinarily boring. Once a fault is found, then we give that to the guys that are experienced and trained to find it and diagnose it. Yeah, and then as I alluded to, again, you can build these levels into your own program. I mean, what we showed you was a suggested program that we call CAST, but it's very easy for you guys to take this on board and build those into yourself. So again, it's about being task qualified is something you'll hear, and task qualified for data collection is very easy to do. Another question I've got here is, what is the norm for the frequency of checks? In the slide I went through in the webinar, we looked at, so most people might do an annual inspection, typically a calendar-based maintenance, or you might have a 5-yearly test schedule where you might only look at something once every 5 years. Especially in the UK, we do that according to the 18th edition. But by looking at the criticality of the equipment that you're looking at and the risk of failure to the organization, those should be the main drivers that dictate what we do. And then we have things like mean time between failure, which is another metrics that we use for dictating how often we may do an inspection. But for me, it's criticality and the risk to business. So if that fails, what would happen to the business? For instance, if you had zero redundancy and you had something that was super critical to the business, you might be doing a quarterly inspection. Yeah, you might be doing a monthly inspection because you might have also seen a similar item within your portfolio fail. So you might all of a sudden want to increase your inspections because of the failures that you've seen in other items. So reliability-centered maintenance goes over that a lot, but I use criticality and risk to dictate how often I may do a piece of equipment. But when with CAST, for instance, because it only takes minutes to do the check and it's on a rounds and reading scenario, we tend to do that every 90 days because literally the guys are only taking numbers and doing data collection. So I hope that answered that for you. Another question we have here is, okay, so can we go directly from an IoT-based solution without implementing an inspection window system? You can. I mean, we have some people that just work primarily on sensors, but again, I suppose I look at it as, if the sensor alarms, how do you qualify that what you're seeing on the sensor is an actual reading? So equate that to your home burglar or a fire alarm system. A fire alarm system will not put the sprinklers on if a smoke alarm goes off, but it will put the sprinklers on if a smoke alarm goes off and it detects heat, because you have two knowns of smoke and heat to dictate that you have a fire, and then it will put the sprinklers on. So why the inspection windows are there is that the IoT systems are there to monitor what's going on, and if they detect, let's say, a heat rise or an ultrasound event, the engineer can go down open the inspection window with an infrared camera and ultrasound equipment. They can actually physically see what's caused that anomaly, yeah, and then dictate, and then whatever they're seeing, depending on the severity of the fault, that would dictate the next thing, whether they shut it down or they can nurse it through, they can reduce load. There's all sorts of things you can do once you are more in the picture of actually what's going on. So what we say is that, the IoT-based solutions are literally that belt and braces. Yeah, they're going to monitor things in between that 90-day schedule, and then if you do see an alarm, it's very easy for you to go in under full load conditions, open the inspection window, take all the readings, confirm what you're seeing on the sensor is correct, and then formulate your next action. So it's a two-pole alarm system through IoT and physical inspection equipment. Another question, and this will probably be our last question. So here we are. Second. There we are. So what are the cost savings associated with calendar-based maintenance? I've just covered that, I think, so that was answered. Frequency. So the last one here is there a possibility that a distributor can do scheduled training? We do have distributors in the field all over the world that do offer these training packages. And again, you can bring in a trainer, and I like to use trainers to underpin my own individual training plan. Okay, so if you looked at the what we covered in the requirements of building your own training or your own management system, you should look at the training required to support your management system and approach either an IRIS distributor or any of your other preferred training distributors and get them involved in building your own training program. So that's it. I think I've run out of time. I have no more time to take questions. There are some more outstanding questions that I will answer online. But thank you again for being part of the webinar and taking time out of your busy days. Thanks for things. Take care, stay safe, and we'll talk to you all soon.